All right, welcome back to our class again. So in this video, we are still on a complex introduction to complex variables, and we are still on complex number. In the first video, we talked about the definition of a complex number, the operations of complex number, the forms of complex number. You can watch the video first before this particular one. The link is on the description, or you go to the playlist site and see a full playlist video on complex numbers. So let's now talk about the Moivre theorem. That's what we have today. Now, the Moivre theorem is very simple. It's just a way of getting the power of a complex number. If you want to get the power of a complex number, we use the Moivre theorem. So remember that a complex number can be expressed in three major forms. And the three major forms is the rectangular or the Cartesian form, which is z is equal to x plus yi. Okay. So another important form is the polar form, which is z is equal to r in bracket of cos theta plus I sine theta. Okay, so the exponential form is z is basically r. You know that the meaning of this is exponential I theta. That's the meaning of this one. So these are basically the three forms of a complex number. We have done that in the previous video, so you can watch that to understand how all these things work. Now, if we want to get the power of a complex number, z raised to power n, how do we do that? Okay, now z raised to power n is the same thing as saying this thing now raised to power n, that is x plus yi raised to power n. So now, anytime you want to get a polar form, the easiest way to get the power of a complex number is to express that complex number in polar form. So if I express this complex number in polar form, it will now be like this. So therefore, z will now be equal to r in bracket of what? In bracket of cos theta plus I sine theta. Okay? So if I'm taking z raised to power n, it will now be all these people now raised to power n. Now let me tell you what the Moivre theorem says. The Moivre theorem now says that z raised to power n will now be this one first, separate them. R raised to power n, then cos theta plus I sine theta, everybody raised to power n. Now the Moivre theorem said that when you have something raised to power n here, that the n should just come and multiply the argument. You understand? It will not come and multiply the angle, the argument. So this is something that saying z raised to power n will now be r raised to power n cos n theta plus I sine n theta. So the n will just come and multiply the theta. So that is what this is what we call the De Moivre theorem. Okay, so this is what we call the Moivre theorem. So I'll give you an example to that. Remember in the last video we solved z is equal to maybe 1 plus I root 3. And then maybe they say you should find z raised to power 4, for example. So the easiest thing is to convert this into a polar form. So to convert it into polar form, the first thing I'm getting is my r. My r is equal to the square root of x squared plus y squared. Okay? So which is what? R is equal to what? The square root of 1 squared plus root 3 all squared. Don't forget that this is your x. The one that is close to I is your y. So therefore, r becomes the square root of 1 plus 3. So r becomes the square root of 4. So my r becomes what? 2. Okay, so the next thing to get is the theta itself. Theta is equal to, I told you before you get theta, it's important to draw the Cartesian plane to know where it will fall. Very important. So this is positive. Your x is positive. Just draw a line on the positive. Your y is equally positive. Draw a line on the positive. They will meet somewhere here. So they met at the first quadrant. So any angle I'm getting for this must be between 0 to what? 90. So that is the importance of drawing this. So I told you, I explained this in the former video. So my theta is equal to what? The tan inverse of y over x. So my theta is now what? Tan inverse of my y is root 3 over 1. So root 3 over 1 is the same thing as root 3. Tan inverse of root 3. And tan inverse of root 3 is what? 60 degrees. Remember that, so the answer will now be, z will now be what? R cos theta plus I sine theta. Don't forget to put your bracket. So my z will now be 2 cos 60 plus I sine 60. So depending. So therefore, z raised to power 4 is something as saying what? 2 raised to power 4, then in bracket of cos 4 times 60 plus what? I sine 4 times 60. Okay? So that is if you decide to leave your answer in degree, but most of the times the answer must be in radian. So the answer must be in radian. So if the answer to be in radian, so that means that my z will now be, I have to convert this 60 to radian. So converting 60 to radian is simply attach pi to it and divide by 1/8. So reduce this to the lowest to give you pi over 3. Okay. So this thing is the same thing as saying the z is the same thing as saying 2 cos pi over 3 plus I sine pi over 3. Okay, like this. So therefore, z raised power n or z raised power 4 will now be this one first. 2 raised power 4 in bracket of cos 4 times pi over 3 plus I sine 4 times the same pi over 3. So that is what the Moivre theorem is saying. So which is what? 2 raised power, this is 16 in bracket of cos 4 pi over 3 plus I sine 4 pi over 3. Okay? Or it will be in this form. 16 in bracket of cos, this is 24, right? 2/4 plus I sine 2/4. Okay? So any of that is the answer. So that is basically what we mean by the the De Moivre theorem. Okay, so now, having known this, let us now talk about the application of De Moivre theorem. How do we apply De Moivre theorem? So write that application of De Moivre theorem before we now move into the main thing we have. The main thing we have is this man, complex variables. So, but all these ones are like prerequisites, like the knowledge you need to have before we move into that complex variables. Okay. So application of the Moivre theorem. Right? Application of the Moivre theorem. Application. So how do we apply this De Moivre theorem? Number one, the first application is the expansion. We apply it in the expansion, to expand or in the expansion of cos n theta and sine n theta. So the Moivre theorem helps us to expand sine n theta. For example, if they say you should expand sine 4 theta or cos 3 theta. So cos n something or sine n something. The Moivre theorem will help you to expand that. So let us see that and see how it works. Okay. So in the expansion of this, now we know that z is the same thing as the polar form. Okay, the polar form z is the same as r raised to power r in bracket of cos theta plus I sine theta. Okay, so but now z raised to power minus 1, which is same as saying 1 over z, right? Okay, which is same as 1 over z, is equal to what? Is equal to, before we do this, first of all, let's set r to be 1. Let's say that r is 1 so that r will not disturb us in what we are doing. So if r is 1, we now have that z is equal to just cos theta plus I sine theta. Okay? So now, z raised to power minus 1 is the same as saying 1 over z, right? Which is equal to what? Cos theta plus I sine theta all raised to power minus 1. If you remember what the Moivre said, that the minus 1 will just come and multiply these people. So this is the same thing as saying cos minus 1 times this will give you minus theta. Okay? Plus I sine minus theta again. So don't forget, I told you before that only cos is an even function. So which means that sine is an odd function. So even function, I mean that minus does not affect it. We can just throw away that minus. So I'm having that this is just cos theta. So, but even odd function means that the minus can come to the back. So this is minus I sine theta. Okay? So let me write out this thing I just wrote. So to write out this thing I just wrote, it means that Z is equal to what? Cos theta plus I sine theta. Okay? So 1 over Z is equal to what? Cos theta minus I sine theta. Okay, so that means if I take the square of this, Z square is equal to saying cos, remember the 2 will come and multiply this, so cos 2 theta plus what? I sine 2 theta. Okay? So now, if I take 1 over Z square, so it will now be the same thing as what? Just change the sign here. Cos 2 theta minus I, just follow me, minus I sine 2 theta. We are going to somewhere. So if we take, this thing has a pattern, so let's generalize this. Generalize it, I mean, is that Z raised to power n is the same thing as saying what? Cos n theta plus what? I sine n theta. So if I take 1 over that, 1 over Z raised to power n is the same thing as saying what? Cos n theta, what? Minus what? I sine n theta. Okay? So now, let's call this equation 1. Okay, let me start from the main one. Okay, let's call this equation. In fact, these two are very, very important. These two are very, very important. And this one as well. Very, very important. The two of them are very important. Okay? But before that, let's call this equation 1 and 2 and add and see what is going to happen. In fact, this is not even the formula I need. This is not the formula I need. So let me call this equation 1, equation 2. So let's add equation 1 and 2 and see what we are going to get. Let's add 1 and 2 and see what we are going to get. Permit me to clean this. Okay? So if we add 1 and 2, add equation 1 and 2. If I add 1 and 2, you see I'm going to be having Z raised to power n plus 1 over Z raised to power n is equal to this plus this will give you 2 cos n theta. Why this plus this is gone? Okay? Very, very important thing to note. Okay? Now, if we now subtract, let's call this equation 3. If we now subtract 1 and 2, subtract 1 and 2. If you subtract 1 and 2, I'll have Z raised to power n minus 1 over Z raised to power n. Will give you, this and this is gone. This minus this will give you 2I sine 2 theta. So, okay. So now, easy. So these are the two. Okay, let's call this equation 3. Equation 3. Very important. Very important. So, okay. Let's call this one equation star. Equation star. And then equation star star. Let's do the same thing here. If we add star and star star, see that I'll have Z plus 1 over Z is equal to what? Just cos theta. Okay, if we subtract it, if you subtract star from and star star, you will see that Z minus 1 over Z will give you I sine 2 theta. Sorry, sine theta. So take note of these two and take note of these two. It will help us in what we want to do. So take note of these two, take note of this, take note of this. It will help us in what we want to do. So now let me do an example to that so that it will help you to do that. Okay? So let me do an example so that you see the application of all this nonsense derivation we have been doing since. So let me give an example. Okay? Example said we should expand cos 4 theta like this. Expand cos 4 theta like this. Okay? Solution. We know that z is same as what? Cos theta plus I sine theta. Remember. And then 1 over z is equal to what? Cos theta minus I sine theta. If I add the two of them, I'm going to have that z plus 1 over z is equal to what? Let's say that z plus 1 over z. Okay, let's say that z is equal to okay, so to add both of them is giving me 2 cos theta. Now, remember that what I'm looking for is raised to power 4. So let me have raised to power 4 of this. So that means take the fourth power of both sides. So I'm going to have z plus 1 over z, okay, all raised to power 4 is equal to 2 cos theta all raised to power 4. Okay, so I'm going to expand this using Pascal's triangle. So if you remember, go and watch my video on binomial expansion. Pascal's triangle said 1, 1, 1 plus 1 is 2, 1, 1, this plus this is 3, this plus this is 3, 1, 1, this plus this is 4, 6, 4, 1, 1. Okay, so I'm using the quotient of 4, which is this one. So to expand anything raised to power 4 is the first one z will be raised to power 4. Do I write it? Let me write it somewhere here so that maybe you'll be seeing it. So I'm going to expand this. To expand this, I'm going to have that this is z raised to power 4 plus the next coefficient is 4. If you take 4, that z will be raised to power 3, and then 1 over z will be raised to power 1, okay, or raised to power 1 like this, anyone you like, plus, so the total of them should be 4. So there is 1 over 4 raised to power 0, but anything raised to power 0 is gone, 1, and so that's why I did not write that. So the next one, the coefficient is 6. If you write 6, the coefficient, the z now will now be raised to power 2, while the 1 over z will now be raised to power 2. So this one will be reducing, this one will be added. So plus the next one is 4. So the z will now be raised to power 1, while the 1 over z will be raised to power what? 3. Then finally, 1. 1 times anything is the same thing. So I'm having just 1 over z raised to power 4. Because the other one will be z raised to power 0, and z raised to power 0 is still 1. So that's why I ignored that. So the expansion of that will now be z raised to power 4 plus 4z squared, because this will take care of one of these to have z squared. So plus 6, because this is z squared. This will take care of each other, gone. So plus what I'm having here is 4 over z, because 1 again, okay, 4 over z squared, 1 up, 2, 3 down. So 1 taking care of 3. I'm having 2 still down. So I have plus 1 over z4. Remember that this thing is equal to 2 raised to power 4 cos 4 theta like this. And remember that this is the man we are looking for. So with this now, let us bring those that look alike together. Okay? Let us bring the like men together. So I'm going to have this person raised to power 4, this person raised to power 4. So I'm going to have z plus 1 over z plus 1 over z, 4 plus, let me have it like this. Okay? Then another person I'm having is what? 4 into z squared plus 1 over z squared. Okay? Then let's 6, okay, plus 6, okay, is equal to what? This raised power, this is what? 16 cos 4 theta. Now, see the reason we are doing this. The reason we are doing this is that remember that if 1 over, okay, remember that 1 over z, sorry, remember that z raised to power n plus 1 over z raised to power n is equal to cos n theta. Remember we proved this. If you remember this, so which means z raised to power 4 plus 1 over z raised to power 4 is that now saying what? Cos 4 theta. Remember? So plus this one will now be what? 4 cos what? cos 2 theta. Then what? Plus 6 is equal to 16 cos 4 theta. So if I make this cos 4 theta, I'm looking for subject. I'm dividing everybody by 16. So therefore, cos raised to power 4 theta will now be 1 over 16 cos 4 theta plus 1 over 4. 1 over 4 cos 2 theta, then plus 6 over 16 will give you 2 here, 3, 2 here, 8. That is 3 over 8. 3 over 8. So sorry about that. My mic went off. So sorry about that. So you see that what I did was just that cos 4. I divided everybody by 16 after changing this to this, changing this to this, and I divided everywhere by 16. So to have that this one will be 1 over 16, this one will be 4 over 16, setting as 1 over 4, 6 over 16, setting as 3 over 8. So you see that the expansion of this is giving us this. So which means that the Moivre theorem will help you to expand this. So let us try for sine. Let's solve one more question for sine. Then we'll now go to the second application. Okay, so let's solve for sine. Okay, so for sine, so they say we should expand sine. Let me use 3 sine 3 theta, because I don't want to waste much time, because I have so many things to do in this video and I don't want it to be too long. So for this particular one, the expansion of sine 3 theta, okay, the expansion of sine 3 theta, we go again. Solution, we know that z, okay, z plus 1 over z is equal to what? Z plus 1 over z is equal to I'm using minus because I'm not using plus, I'm using minus because minus give us sine, is equal to I sine, is it I sine theta? Sorry, 2I sine theta. Yes, 2I sine theta. So you can derive it again if you have forgotten. Okay, so this gave us this, or to derive it again is simply to start with your normal. To derive it again, start with your z is equal to cos theta plus I sine theta. And then your 1 over z is equal to cos theta minus I sine theta. So the only thing that will still remain the cos is to subtract. If I subtract this and this is gone, so that will remain the sign. So this and this is gone, the sign will remain because I'm interested in the sign. So therefore, z minus 1 over z is equal to this plus this will give you 2I, because minus minus is plus. This plus this is now 2I sine 2 theta. Okay? Now, I am looking for raised to power 3. So let me take the cube of both sides. So I have z minus 1 over z all raised to power 3 will now be equal to 2I sine, sorry, not 2 theta. Okay, yes, sine 2 theta. How did I get 2 theta? Sine theta. It's just these two adding each other. So sine theta. Then raised to power 3. Sorry about the mistake. Okay, so expand this one by binomial. Binomial said 1, 1, 1 plus 1 is 2. You add 1 in the front, add 1 at the back. This plus this is 3. This plus this is 3 again. Add 1 in the front, add 1 at the back. So I'm using this particular one. So to expand this means the first one will be raised to power 3. The other one will be raised to power 0. But anything raised to power 0 is gone. So I'm not attaching it. Plus, the next one I'm taking 3. So this one will now reduce to z squared. While the other one will now come, there is minus in it too. So minus 1 over z will now be raised to power 1. Then plus the next thing is 3 again. 3 again, I'm having z will now be raised to power 1. Y minus 1 over z will now be squared. Then plus this one will now be 0. So it's gone. So I'm now left to just minus 1 over z raised to power 3. Okay. So the expansion will now give me z raised to power 3 minus 3 over z, because this take care of 1 over this. So this and this, okay, 1 2 3 4. Okay, this will give you minus 1 over z. No, I'm not correct. This is z cube. 2 and taking care of 1 is 3z. So this is minus 3z, sorry, minus 3z. Okay, so 2 down and 1 up is 1 remaining down. So but minus squared is plus. Minus squared is plus. So I am left with plus 3 over z. Plus 3 over z. Then this one will now be minus 1 over z cube. Okay, is equal to here. So this thing is equal to what? 2i all cube, and then sine cube theta for the other side. So, and 2i all cube will give you, 2 cube will give you 8. I cube, remember I told that I cube, I is 3 is an odd function, so I'm expecting, so it's odd, sorry. I'm expecting I or minus I. If I divide 3 by 2, I'm having 1.5. So, but I don't need the point, so it's 1. So this one is odd. So I'm taking minus I. So this is minus 8I. So go and watch the first video. You understand how I got that I raised power 3 is minus I. So I will now have sine cube theta. Okay. So now with this, I will now have with this, let me get the people that look alike together. So I have z raised to power 3 minus 1 over z raised to power 3, like this. Then plus, I'll go again, sorry. Okay, plus 3. If I bring up plus 3 divided by this, I'm having, I want to, okay, let me have minus 3 here. Minus 3 divided by this, I'm having z here. Minus 3 divided by this, I'm having minus 1 over z. Okay, is equal to minus 8i sine cube theta. Okay, so now remember that if I have z raised to power n minus 1 over z raised to power n, that is must give me 2i sine that n theta. Don't forget. So which means this side will give me 2i what am I talking about? Yes, this side will give me 2i sine 3 theta. Okay, minus 3 into this side will give me, it's obvious, this side will give me 2i sine theta. Okay, so it's equal to what? Minus 8i sine cube theta. Okay, so with this, you will see that divide everybody. Okay, let me open the bracket. This is 2i sine 3 theta minus 6i sine theta is equal to what? Minus 8i sine 3 theta. So if I divide both sides by 8i, divide everybody by 8i, so that my sine cube theta that I'm looking for will now stay alone. So if you divide this by 8i, I take care of it will now be 2i over 8i. So I take care of I have 1 over 4 remaining. So I have 1 over 4 sine 3 theta minus, I have 6i over 8i. I take care of I, 2 here, 3, 2 here, 4. So I have 3 over 4. So 3 over 4 sine theta. So that is that. So the expansion of this is now this. So you see, the Moivre theorem helps us to expand sine n theta and cos n theta. That n, I mean, is as power. Okay, so let's now move to the second application of the Moivre theorem. So the second application of the Moivre theorem. Okay, permit me to refill my marker, then we'll go again. So please, if you have watched this video to this point, please don't forget to like, share, subscribe if you are new, and drop your comments. Tell us if you are enjoying our class. Okay, so we go again. So the second application. So this is the second application of the Moivre theorem. Okay. So the second application of the Moivre theorem is in the expansion. It helps us to expand cos n like this theta and sine n like this theta. Remember that the other one was cos power n theta like this and sine. The n was as power, but this time around is no longer as power. Okay. So now, to do this, what do we do? Okay, let's go back to what we know. We know that z plus 1 over z is equal to what? Is equal to, what am I talking about? Is equal to sine. Okay, is equal to what? Let's start from the small ones before we start. So we know that z normally is equal to what? Cos theta plus I sine theta. And then we know that 1 over z is equal to what? Cos theta minus I sine theta. Okay, so that means that z plus 1 over z is equal to what? Cos theta 2 no, I'm not adding. Let me take the power. So I know that z raised to power n is the same thing as what? Cos n theta plus I sine n theta. Okay? So now, this thing means that the cos n theta I'm looking for. I hope you know that this one is the real part. This is the real part. The real. Why this one is what? The imaginary part, because it has I imaginary. So that means whenever you have z raised to power anything at all, the real part is what we call the cos theta. So therefore, cos theta, or cos n theta is equal to just the real part of z raised to power n. Okay, while sine n theta is equal to the imaginary part of z raised to power n. So this is just basically the two things we need. Okay, this is basically the two things we need. Okay, so example. Can I clean here? Yes. So just write this, and then it's very easy. So let me give you an example. Example will help us to do that. So they say expand, question number 1, expand cos 5 theta. Okay, expand cos 5 theta. So now the first thing we need to do, solution is that we know that our z is equal to what? R is not there, so it's just cos theta plus I sine theta. Okay, so now z raised to power 5 is the same thing as cos theta plus I sine theta raised to power 5. Okay, so if I'm looking for cos 5 theta now, cos 5 theta is simply the real part of this man, the real part of this cos theta plus I sine theta. So if I expand this normally, then raised to power 5. So if I expand this normally, I will not apply the Moivre theorem. So if you apply the Moivre theorem, it's just to multiply this and multiply this, which the real part is simply just this. So, but let us expand this normally and then see what the real part will give us. So expanding this normally, first of all, let us expand it normally, then we'll not take the real part. So if we want to expand, let us expand cos theta plus I sine theta all raised to power 5. Let us expand it, then we'll not take the real part, because the real part is the cos. Okay, so expanding this will give us normally, let's use a Pascal's triangle. 1 1 2 1 1 3 3 1 1 4 6 4 1 1 5 10 10 5 1 1. So we're taking 5 10 10 5 1 1. So 1 first. 1 is the first one, cos 5 theta. Okay, cos 5 theta plus 5. Now 5 will give you cos 4 theta, then in bracket of I sine theta raised to power 1. So this will now be 4, this one will be 1. Or let me write it this way: cos theta raised to power 5, then cos theta raised to power 4. I think you understand it better like this. Remember, there is 5 at the back, plus 5. Okay, so the next one is 10. So plus 10, I will now have that what? Cos theta will now be raised to power 3, while I sine theta will now be raised to power what? 2, plus the next one. The next one is 10 again. So I have 10. 10 will now be in bracket of cos theta. Cos theta will now be raised to power 2, while our I sine theta will now be raised to power 3. Okay, plus the next one is 5. 5 cos theta will now be raised to power 1, while our I sine theta will now be raised to power 4. Then finally, I will now have I sine theta to be raised to power 5. Okay, so now the answer to this becomes, let me start from here. This is equal to, this is now cos 5 theta, okay, plus here I will come outside because I raised to power 1 is I. So I have 5I, then cos 4 theta sine theta. Now, I squared is minus 1, so which will make this place to be minus 10. Minus 10 cos 3 theta sine 2 theta. Okay? So now, I raised to power 3 is minus I. So this is minus 10I cos squared theta sine cube theta. So I raised to power 4 is 1. So this is something as 5 cos theta sine theta. Then I raised to power 5. I raised to power 5. I'm expecting, this is odd number, I'm expecting I or minus I. Divide this by 5. I have by 2, sorry, 2.5. So I'm not interested in the point 2. So I'm taking even number I. So this is plus I sine 5 theta. So remember that we are only interested in the real part, the one that does not have I. So therefore, our cos 5 theta is only the real part. So remember that our cos 5 theta we are looking for is just the real part of this expansion. The real part of this cos theta plus I sine theta raised to power 5. Okay, so let's take only the real part. The real part is the one that does not have I. So how this is now what? Cos 5 theta. This one has I, we don't need it. This one does not have I, so I have minus 10 cos 3 theta sine square theta. So this one has I, we don't need it. So this is the last one we need. Plus 5 cos theta sine 4. Sorry, there is 4 here. Sine 4 theta. Sine 4 theta. So sine 4 theta. Okay, so that is the answer. So the expansion of this is the real part of this. So one more example, then we'll now go to the last application of, we have those 3 applications. So the expansion of this is this. Okay, so we'll go to the next one. So the next one is, let me look for a smaller one. Maybe expand sine. Let's check the sine part. Expand sine 3 theta. So this one is too long. So let's go to expansion of sine 3 theta. Okay. So we know that solution. So we know that z is equal to what? Cos theta plus I sine theta. Remember that arrow is supposed to be here, but since we are doing this expansion, we are taking arrow to be 1. That's why we are ignoring our arrow. Our arrow is not necessary in this part. Okay? So now we know that z raised to power n is equal to what? Cos theta plus I sine theta raised to power n. So which is something as z raised to power n is equal to cos n theta plus I sine n theta. So you see that sine is the imaginary part. This one is the real part. This one is what? The imaginary part. So anytime we want to get sine something, we expand that thing with normal binomial expansion, and we now take only the imaginary part of it. The imaginary part of it becomes our expansion. So let us do that. So to do that now, we're having that. So we have that sine 3 theta, okay, is the same thing as saying the imaginary part of just cos theta plus I sine theta raised to power 3. Or if you don't know it this way, just start with sine theta plus cos theta plus I sine theta. Okay, so then z raised to power 3, because we have 3 here, will now be cos theta plus I sine theta raised to power 3. So which is z raised to power 3 is equal to what? Cos 3 theta plus I sine 3 theta. So you will now notice that this one is the imaginary part of this thing. So therefore, sine 3 theta is simply the imaginary part of this expansion. The imaginary part of expansion of cos theta plus I sine theta raised to power 3. You see that? So which means if I expand this normally with binomial expansion, then the next thing I will do is what? To get the imaginary part. So let us now expand it normally. So the expansion is cos theta plus I sine theta raised to power 3. So according to binomial 1 1 Pascal 1 1 3 3 1 1. So I'm taking 1 3 3 1. So 1 is 1 raised to, so this is cos, it will start from 3 theta. Why this one will start from 0? Or let me write it very well. Cos theta all raised to power 3. Why this one will start from 0? But any 0 raised to power 0 is 1. So I'm not interested. Plus 3. I'm taking 3. I will now have cos theta will now be squared. Why the I sine theta will now be raised to power 1. Okay? Plus, we go again 3. We have the cos theta again to now be raised to power 1. Why the I sine theta will now be raised to power 3. Sorry, will now be raised to power 2. Right? But this one will be reducing, this one will be added. So finally, plus 1. But I'm not interested in the 1, so I have 1 I sine. Okay? So if I expand that, I'm going to be having this one will now be just cos 3 theta plus this one will now be I raised to power 1 is I. So this is 3I cos squared theta, then sine theta. You see that? So in this one, I squared is minus 1. So I'm having minus 3 cos theta sine squared theta. Then finally, I raised to power 3 is minus I sine cubed. Okay, so I'm looking for sine 3 theta. So sine 3 theta is simply the imaginary part of this expansion. Imaginary part of I sine theta raised to power 3. Okay, so its imaginary part is to take only those that has I, which is just these two people. Only those that has I, which is just these people. So the expansion of that is what? 3 cos theta, or let's just say, okay, remember I expanded this there here, and then write them with I so that I can cancel I, or just take only those that has I but don't include the I. So this one has I cos theta. This person has I again minus sine cube theta. So the expansion as simple. So now, I move to the theory. Is remaining 10%. Video it a little bit. Okay, so let's continue. Let's manage. I pray it will not off because trying to charge it will take my time. So let's move to the last application of the Moivre theorem. Okay, so the last application of the Moivre theorem is in the nth root of a complex number. So number 3, the Moivre theorem helps us to get the nth root of a complex number. Okay. All right. So now before we talk about the nth root of a complex number, let's take some few properties of sine and cosine. Okay. The sine and cosine graph. Now for sine graph, let's have this as our x and y plane. This is y and this is x. Okay. So we now have that you know that the sine graph goes this way. The sine graph goes, it starts from 0 because sine 0 is 0. So it starts from 0, move this way, this way. Okay, let me keep going. So let me keep going. Don't mind my own, oh, sorry about that. Okay, so this is your sine graph. Okay, this is sine x. So sine x is given this way. You should know that from this point to this point is half of a second. And I told that the angle for half of a circle is 180. Half of a circle is 1 because the total circle is 360. And 180 radian is certain as pi. So here is pi. From here to here is another pi. So we call it 2 pi. Here to here is another pi, which is what? 3 pi. Here to here is another pi, which is what? 4 pi. Here to here is another pi, which is what? 5 pi. And so on and so on and so on and so on. Okay? So now, the next thing we're going to get is the periodic of sine x. So what is now the periodic of sine x? The period of sine x is that is the time it will take you to complete a circle. Okay, it's called the period. The time it will take the wave to move to a complete circle. If you join half of this and this to make it a complete circle, so this is the period of it. Okay, so you see that the period is what is 2 pi. So each period is 2 pi, 2 pi. So another period is from here to somewhere here. Is another period, which is, let's call it 2t. So another period is from here to another one. So we have up to nt. Okay. So now, so the period of so let's write sine x in periodic form. So to write sine x in periodic form, so the periodic form of sine x. So the periodic sum of sine x is that y is equal to sine x plus t. So the time it will take you to complete one oscillation. Okay, one oscillation is the complete circle. So, and remember that t is the same thing as saying from here to here, which is 2 theta, 2 pi, sorry. So which is what? Y is equal to what? Sine x plus 2 pi. Okay, so and you see that this thing continues up to many of them, any number of it. So any number of it is to have that y is equal to sine x plus any number of periods. Any number of periods we are going to have. So therefore y is equal to sine x plus what? Sine x plus what am I? 2n pi. Okay, very important. So the periodic form of sine x is what? Sine x plus 2 pi, 2n pi, 2n pi. So now let us now draw for cos and see what happened for cos. I have to be checking if, okay, it's still moving. So let's be fast so that I'll complete what I want to do before it goes off. So I have this. This is my, I want to draw for cos. Now for cos, let's say that here is 1. You know that cos 0 is 1. So cos starts this way. Cos starts this way. Like that. Okay, and on and on and on. So you see that from here, this is not up to 1. This thing. So let's say somewhere half here is our pi. From here to somewhere half here is our pi. Okay, then another half here, from half here to another half here is our 2 pi. From half here to another half here is our 3 pi, like that, and on and on and on. So you see that it's the same thing with sine. So it's the same thing. So to write the periodic form of cos, periodic form of cos x will now be that y is equal to what? Cos x plus t. So which is what? Y is equal to cos. So for it to complete one oscillation is still 2 pi. So which is x plus what? 2 pi. Okay. So and it has any number of it. To get any number of it, you have that y is equal to what? Cos x plus nt. So which is same as what? Y is equal to cos x plus 2n pi. Okay. Cos x plus 2n pi. Now, where n is called the complete circle, that is the number of oscillation, the counter, the number you want to count, okay? The counter or the number of oscillation, okay, or number of complete circle, anyone. Now, why are we studying this? Let me show you why we are studying this. Okay, permit me to clean here. Okay. Now remember, in your de Moivre theorem, let's go back to de Moivre theorem because this is application of de Moivre theorem. So in your de Moivre theorem, we know that we want to get the nth root of a complex number. And in de Moivre theorem, we have that z is equal to what? R in bracket of what? Cos theta plus I sine theta. So now, let us express theta in periodic form. Let us express sine and cos, let us express sine and cos in periodic form. So this is now what? Z is equal to what? R in bracket of what? Okay, let's use this kind of bracket. R in bracket of what? Cos theta plus 2n pi. Don't forget. But let me now, let me change it to 2k pi because you can use any alphabet. 2k pi plus I sine the same what? Theta plus 2k pi. Okay? So we have this. So now, remember that if we want to take the power now, let's say the nth power, z raised power 1 over n, it will now be what? R raised power 1 over n into cos theta plus 2k pi, okay, plus I sine theta plus 2k pi, all raised power the same 1 over n. But de Moivre said that the 1 over n can just come and multiply the thetas. You know that this thing is now, everything here is now our new theta. Everything here is now our new theta. So this is something that says that z raised to power 1 over n. See the reason I change it to k because I don't want the n to conflict. So I have r raised to power 1 over n will now be what? Cos 1 over n into theta plus 2k pi, okay, like this, plus I sine 1 over n into theta plus 2k pi. Okay, so that is that. Why some people will write it 2k pi over n is the same thing, 2k pi over n is the same thing. Okay, so where k is known as the counter, okay, where k is the counter, where k is equal to count, and that counter we mean is from 0, 1, 2 up to n minus 1. It stops at n minus 1. Okay, so now what is the application of this? So anytime you want to get the root of a complex number, we apply this. Let me check if it's still moving. It's still moving. So let's take one or two examples quickly and then we are done. One or two examples. So remember this. So now look at what we mean by that. If we have, we'll take small examples so that we'll not solve too much. So say we have, they say find find z if